When dealing with three-phase 480 volts motor circuits and needing to reverse the motor's rotation for interchangeability due to mechanical design differences, there's a debate on whether to swap leads at the motor or at the plug. The recommended method is to swap the leads directly at the motor. This is because, firstly, safety is a primary concern. Swapping leads at the plug could create a potentially hazardous situation, particularly if the plug isn't properly oriented. By performing the swap at the motor terminals, the risk of incorrect wiring is significantly reduced. Secondly, consistency is maintained across different units. Regardless of the mechanical design variations, swapping leads at the motor ensures that the wiring configuration remains uniform. This uniformity simplifies troubleshooting procedures and overall motor maintenance. Thirdly, convenience plays a role. Swapping leads at the motor is generally more accessible than trying to manipulate connections at the plug, especially if the plug is located in a hard-to-reach area. To reverse the motor rotation, follow these steps. 1. Always disconnect the power supply to ensure electrical safety. 2. Access the motor's terminal box and identify the terminals labeled tone T2 and T3. 3. Physically swap the leads connected to terminals tone and T3. 4. Securely close the motor's terminal box and then carefully reconnect the power supply. By following these steps, the motor's rotation will be reversed safely and effectively. It's important to always prioritize safety when working with electrical equipment. Double-check all connections and ensure that the power is disconnected before making any changes to the wiring. If you are not comfortable working with electrical equipment, consult a qualified electrician. A proper wiring can lead to electrical shock, fire, or damage to the equipment. Remember to always refer to the motor's documentation for specific wiring diagrams and safety instructions. Motor wiring can vary depending on the manufacturer and model. The information provided here is for general guidance only and should not be considered a substitute for professional advice. The NEC, or National Electrical Code, provides detailed guidelines for safe electrical installations. It's essential to be familiar with the relevant sections of the NEC when working with motors and electrical circuits. For example, NEC Article 430 covers motors, motor circuits, and controllers. It provides requirements for motor overcurrent protection, motor disconnecting means, and motor control circuits. NEC Table 430.52 provides guidance on the maximum rating or setting of motor branch circuit, short circuit, and ground fault protective devices. NEC Section 430.22 addresses the ampacity of motor branch circuit conductors. These are just a few examples of the many NEC requirements that apply to motor installations. Always consult the latest edition of the NEC for the most up-to-date information. In addition to the NEC, there may be local electrical codes and regulations that apply to motor installations in your area. It's important to be aware of and comply with all applicable codes and regulations. Ignoring these codes can result in fines, penalties, or even legal action. When working with three-phase motors, it's important to understand the phase sequence. The phase sequence refers to the order in which the voltage peaks occur in each of the three phases. The correct phase sequence is necessary for the motor to rotate in the intended direction. If the phase sequence is incorrect, the motor may run in reverse or not run at all. Phase sequence indicators can be used to verify the correct phase sequence. These devices typically have three leads that are connected to the three phases of the power supply. The indicator will then display the phase sequence, such as a BC or CBA. If the phase sequence is incorrect, the leads can be swapped to correct the problem. Another important consideration when working with motors is motor overcurrent protection. Overcurrent protection devices, such as fuses and circuit breakers, are designed to protect the motor and the electrical circuit from damage caused by excessive current. Overcurrent can be caused by a variety of factors, such as motor overload, short circuits, or ground faults. The overcurrent protection device should be sized appropriately for the motor's full load current. NEC Table 430.52 provides guidance on the maximum rating or setting of motor branch circuit, short circuit, and ground fault protective devices. It's important to choose the correct type and size of overcurrent protection device to ensure adequate protection. In addition to overcurrent protection, motors also need to be protected against undervoltage. Undervoltage occurs when the voltage supply to the motor drops below a certain level. Undervoltage can cause the motor to overheat and potentially fail. Undervoltage protection devices, such as undervoltage relays, can be used to protect the motor against undervoltage. These devices will typically trip the motor starter if the voltage drops below a preset level. Motor starters are used to start and stop motors. They typically consist of a contactor, overload relay, and other control components. The contactor is an electrically operated switch that connects and disconnects the motor from the power supply. The overload relay protects the motor from overload conditions. If the motor draws excessive current for an extended period of time, the overload relay will trip the contactor and disconnect the motor from the power supply. Motor starters are available in a variety of sizes and types to suit different motor applications. When selecting a motor starter, it's important to consider the motor's voltage, current, and horsepower rating. Motor control circuits are used to control the operation of motors. These circuits can be as simple as a start-stop push-button station or as complex as a programmable logic controller, also known as a PLC-based control system. Motor control circuits typically include components such as push buttons, selector switches, relays, timers, and PLC. These components are used to control the starting, stopping, reversing, and speed of the motor. Motor control circuits can be designed to provide a wide range of functions such as automatic starting, stopping, and reversing, as well as speed control and monitoring. When designing a motor control circuit, it's important to consider the specific requirements of the application. The circuit should be designed to provide the necessary control functions while also ensuring the safety of the equipment and personnel. Motor grounding is an important safety consideration. Grounding provides a path for fault current to flow back to the source, which helps to protect against electrical shock. All metal parts of the motor, such as the motor frame and conduit, should be properly grounded. The grounding conductor should be sized according to the NEC. NEC Section 250.122 provides guidance on the sizing of equipment grounding conductors. Motor maintenance is essential for ensuring the reliable operation of motors. Regular maintenance tasks include inspecting the motor for damage, cleaning the motor, lubricating the bearings, and checking the motor's electrical connections. It's also important to monitor the motor's performance and look for signs of problems such as excessive vibration, noise, or heat. By performing regular maintenance, you can extend the life of the motor and prevent costly repairs. When working with motors, it's important to use the proper tools and equipment. This includes insulated screwdrivers, pliers, and wrenches, as well as a multimeter for measuring voltage, current, and resistance. It's also important to wear appropriate personal protective equipment, also known as PPE, such as safety glasses, gloves, and hearing protection. By using the proper tools and equipment and wearing appropriate PPE, you can reduce the risk of accidents and injuries. When troubleshooting motor problems, it's important to have a systematic approach. Start by gathering information about the problem, such as when it occurs, what symptoms are present, and what has been done to try to fix it. Then, use a multimeter to check the motor's voltage, current, and resistance. Also, inspect the motor for damage such as loose connections, burned windings, or damaged bearings. By systematically troubleshooting the problem, you can identify the cause and take corrective action. Motor efficiency is an important consideration, especially for large motors that operate for extended periods of time. High-efficiency motors use less energy to perform the same amount of work, which can save you money on your electricity bill. The efficiency of a motor is expressed as a percentage. For example, a motor with an efficiency of 90% will convert 90% of the electrical energy it consumes into mechanical energy. The remaining 10% is lost as heat. When selecting a motor, it's important to consider its efficiency rating. In general, higher efficiency motors are more expensive, but they can pay for themselves over time through energy savings. Motor horsepower is a measure of the motor's power output. 1 horsepower is equal to 746 watts. The horsepower rating of a motor is typically indicated on the motor's nameplate. When selecting a motor for a particular application, it's important to choose a motor with the appropriate horsepower rating. If the motor is too small, it will be overloaded and may overheat. If the motor is too large, it will be less efficient and may waste energy. Motor speed is another important consideration. The speed of a motor is typically measured in revolutions per minute or RPM. The speed of a motor is determined by the number of poles in the motor and the frequency of the power supply. For example, a 4-pole motor operating on a 60 Hz power supply will have a synchronous speed of 1800 RPM. Motors are available in a variety of speeds to suit different applications. Motor torque is a measure of the motor's rotational force. Torque is typically measured in pound-feet or Newton-meters. The torque produced by a motor depends on the motor's design and the current flowing through the motor windings. When selecting a motor, it's important to consider the torque requirements of the application. Some applications require high starting torque, while others require high running torque. Motor bearings are an important part of the motor. The bearings support the rotor and allow it to rotate freely. Motor bearings are typically lubricated with grease or oil. It's important to lubricate the bearings regularly to prevent wear and tear. The type of lubricant used depends on the type of bearing and the operating conditions. Motor windings are made of copper or aluminum wire. The windings are insulated to prevent short circuits. Over time, the insulation on the windings can deteriorate, which can lead to motor failure. Motor windings can be tested with a multimeter to check for shorts, grounds, and open circuits. Motor cooling is important for preventing overheating. Motors generate heat as they operate. If the heat is not removed, the motor can overheat and fail. Motors are typically cooled by air or liquid. Air-cooled motors have a fan that blows air over the motor windings. Liquid-cooled motors have a jacket that surrounds the motor windings. The jacket is filled with a liquid coolant, such as water or oil. Motor enclosures protect the motor from the environment. Motor enclosures are available in a variety of types to suit different applications. Some common types of motor enclosures include open drip-proof, totally enclosed fan-cooled, and explosion-proof. Open drip-proof enclosures are designed to protect the motor from falling objects and dripping liquids. Totally enclosed fan-cooled enclosures are designed to protect the motor from dust, dirt, and moisture. Explosion-proof enclosures are designed to prevent explosions from occurring inside the motor. Motor nameplates provide important information about the motor, such as the motor's voltage, current horsepower, speed, and enclosure type. The nameplate also includes the motor's manufacturer and model number. The nameplate information is essential for selecting, installing, and maintaining the motor. Motor standards are developed by organizations such as the National Electrical Manufacturers Association, known as NEMA, and the International Electrotechnical Commission, known as the IC. These standards define the performance, safety, and interchangeability requirements for motors. Motor standards help to ensure that motors are safe, reliable, and efficient. Motor applications are diverse. Motors are used in a wide variety of applications such as pumps, fans, compressors, conveyors, and machine tools. The type of motor used in a particular application depends on the specific requirements of the application. Motor technology is constantly evolving. New motor technologies are being developed to improve motor efficiency, performance, and reliability. Some examples of new motor technologies include permanent magnet motors, switch reluctance motors, and synchronous reluctance motors. These motors offer improved efficiency and performance compared to traditional induction motors. When working with motors, always follow safe work practices. This includes disconnecting the power supply before working on the motor, wearing appropriate personal protective equipment, and using the proper tools and equipment. By following safe work practices, you can reduce the risk of accidents and injuries. It is recommended to consult with a qualified electrician or motor specialist if you have any questions or concerns about working with motors. Always adhere to local electrical codes and regulations for any motor installations. Remember to always prioritize electrical safety when working with any type of electrical equipment.